Okay, so up here on the board, I have just some of the different transition metals and stuff like that, and I'm putting them up there so you can see. Again, if you're curious about technetium, technetium is Tc. It's one of the first radioactive elements. The quick way to do that would be to go backwards to the nearest noble gas, and you have to go backwards. So technetium would be with krypton. These two electrons, fifth period, and it's the S block, so that's the 5s2 part. And then the D's, this number -1. So yttrium here begins the 4D, and you literally just count. So 4D1, 4D2, 43, 44, 4D5. So that's why technetium has a 4D5. So even the more complicated ones, like the newest ones, Medarium and stuff like that, you can use these same patterns. Just remember that the S's and the P's will follow the period number. The D's are period number -1, so you can see like this was 6 period, 6 minus 1 would be 5, and the F's would be period number -2. Cool. Two more things I really want to talk about. First one is making an electron configuration for an ion. And when you make an ion, you can either take away electrons to make a cation, or in the case of an anion, a negative electron, you would add electrons to it. And adding an electron to make an anion is pretty simple. You would just follow the normal N+L rules. So this is an example of turning phosphorus on the left into phosphide. Now we've seen that phosphide, which is phosphorus as an anion, phosphorus likes to be -3. And back in the beginning of this class, anything in group 5, 5 minus 8 would be the charge on it, -3. Well, the reason why it's -3 is you're filling in that outer orbital, the outer subshell. So you can see that in phosphorus, there were like 3 places to put electrons. So you can put 1, 2, 3 electrons in there like that to fill it up. So making an anion, you just follow the regular rules of adding electrons in. So you just fill in this case, the 3p to make it 3p6, and you're good to go. Chlorine, number 17, becomes -1 chloride, because there's one more electron space to fill in the 3p's. And sometimes people say the noble gases, well, this is what I say anyway, they're the cool kids in the back of the bus, because all of the elements kind of want to be like them. Well, here we're seeing phosphorus wants to be like argon. When it becomes phosphide, it fills in those outer electrons. And chlorine becomes chloride by adding 1 electron to be like argon. So that's why these electron configurations for the noble gases are pretty important. And most of the time, the cations and the anions will both want to be kind of like them. Any questions on that? Now, cations means you take away electrons, all right? So cation means you're going to have something positive. Now, when it comes to taking away electrons, all right, you want to take them from the highest n orbital first. And if there's a tie, then highest n+L. Now, highest n+L means last one's in, first one's out. But we're going to see that because highest n is even more important, that's not always the case. So let's look at what happens here when phosphorus becomes a phosphorus +3. Phosphorus +3 means we need to take away 3 electrons. And usually, last ones in are the first ones out. So as we fill in electrons, the 3p3 were the last ones we filled in. We're going to pull those 3 electrons out. That's the highest n+L. Highest n+L means last one's in, first one's out. It's not highest n because 3s and 3p have the same n number, all right? So it's like a tie for that one. But highest n+L means last one's in, first one's out. Phosphorus +3 would be neon 3s2. So those 3 electrons will be the first ones out in this case. It's not highest n because the n's here are tied, but highest n+L means 3p comes out before 3s. Any questions on that? All right. why this part is important is because of transition metals, and we'll talk about that here in a little bit. Now this one's kind of interesting. It says the electron configuration 1s2, 2s2, 2p6 represents which of the following? All right? So first of all, for a neutral atom, what does this electron configuration represent? Remember, you can either add up the electrons and find the number on the periodic table, or the outer one here is a 2p6. So neon, well done, that's right. So if it was 2p6 you were looking at, the right-hand side, those are all p block. Second one would be 2p, so 2p6 would be neon, and that's a totally cool way to do it. But you can also literally just add up the electrons. So 2 plus 2 plus 6 is 10, and 10 electrons, good old neon there in the upper right-hand corner. So one of them is going to be neon, all right? That's the neutral neon electron configuration. But check this out. 1s2, 2s2, 2p6, 3s1 is the electron configuration for neutral sodium that we saw earlier. And one of the options up here is sodium plus 1. Now, if you're taking away electron, highest N is the one that comes out first, and 3 is higher than 2 or 1. So sodium plus 1 is going to lose that 3s1. So 1s2, 2s2, 2p6 is also sodium plus 1. And let's do magnesium first. Neutral magnesium, 12 electrons, 2 plus 2 plus 6 is 10, plus 2 more would be 12. Highest N to make positive 2 magnesium. Highest N again here. Guess what? 1s2, 2s2, 2p6 is magnesium 2 plus as well. So we've already got neon, magnesium 2 plus, and sodium plus are that way. Oxygen, 1s2, 2s2, and 2p4, and I'm going to write it here as an orbital box. And by the way, I'm a lazy chemist. My line is like a box in the diagram. You can do it either way. And these are what they call half arrows. It's a way that nerdy chemists write about things. But anyway, 2p4, this would be 1, 2, 3, 4 electrons. Now to make oxide, O negative 2, you have to add 2 more electrons. You'll put them in the first spots available, which would be to pair up these 2 electrons. So guess what? Oxide also 1s2, 2s2, 2p6. So all 4 of those, all right, have a neon configuration. And this is why I jokingly sometimes say that, that should be it. Oh, there's 2. That's why I sometimes say the noble gases are like the cool kids in the back of the bus. All these other atoms usually want to be like the noble gases. So magnesium will lose 2 electrons, oxygen will gain 2 electrons, all right? That's not all the time, but it's a kind of a fairly common kind of a rule and stuff. It definitely works well for all the main group metals and the non-metals. So like sodium is always plus 1 and potassium is always plus 1 because they're going to be like noble gases. Any questions? All right. Transition metals also make positive ions usually, all right? And remember the rule is highest N first, then highest N plus L, blah, blah, blah. Now, iron is argon 4s2 3d6. And this is where it's interesting. Iron plus 2 means remove 2 electrons. And highest N means 4s comes out before 3d. Now, why I want you to think about this is because when you fill in electrons, all right, it goes argon, and then 4s2, you get to calcium, and then add 6 more electrons to get to iron. The 4s's were not the last electrons in, but they are the first electrons out because highest N comes out before highest N plus L. So when it comes to the transition metals, they'll often lose those s electrons first and then start taking away the d's. So making iron plus 2 from iron, the 4 s's are gone. Highest N. N of 4 is higher than N of 3 and 3 does. After you remove those two, for example, to make iron plus 3, then you can start taking away the last one's N. So 3d6 becomes 3d5, going from iron positive 2 to iron positive 3 because of that. But again, when you make initially, the 4 s's will be the first ones out, highest N. After that, then you can start taking away the 3d's. I see this a lot of times, like people will say, all right, iron to argon 4s2 3d6, and making iron plus 2, you'd have argon 4s2 3d4. Highest N comes out first. The idea is that higher N is farther from the nucleus and not held on as well. If you believe that or not, it's up to you. But that's the idea. Highest N, 4s, comes out before 3d. Any questions? Magnetism is a big part of transition metals, lanthanides, and actinides, all right? And knowing how many electrons are there becomes really important. Now, this neutral zinc has 4s2, 3d10, but zinc plus 2, you lose those two 4s electrons, and you just have 3d10. Zinc positive 2, every up is a down, so that would be a diamagnetic ion. On the other hand, we saw iron plus 2 earlier. The 4 s's were removed. This one actually has 1, 2, 3, 4 unpaired electrons. It has a total of 6 electrons in the 3D shell. The 2 of them are pairs. There would be 4 of them. Manganese plus 2 is an example of something with 5 unpaired electrons when the 4 s's are removed. So an orbital box notation can literally tell you how many unpaired electrons there are. We would say that manganese plus 2 by default is the most paramagnetic because it has 5 unpaired electrons. 4 unpaired electrons is certainly paramagnetic, but in theory not as paramagnetic as something with 5 unpaired electrons. Any questions? So here's a kind of picture, here's a kind of problem you might see. It says what ion represents the following electron configuration. And if you look at this carefully, it's got an empty 4s shell. This is argon and 3d. Now, I want to focus on the argon and 3d here real fast, because if you look at this list of possible answers, rhodium, all right, rhodium is number 45, and it is in the 5th period. If you went backwards, rhodium would have some kind of a krypton core, all right? So this is not going to be rhodium. Rhodium would have a Kr right there instead of an argon, all right? These would all be filled in if this was rhodium. Rhodium would have a 3d10, 4s2, 4p6, etc., etc. So it's not that. Another one that's worth looking at real quickly here is calcium positive 2. Now calcium is number 20, and if it loses 2 electrons, you can go back to number 18. Calcium would have just an argon core. It wouldn't have any 3Ds or any 4Ss, so it certainly is not calcium 2+, and it's not rhodium 3+. Questions on either one of those? Nickel, cobalt, and iron are all in the 3D period. The 3Ds, once again, is the top row of transition metals. So it's going to be one of those 3, all right? And what I would try to focus on, because the 4s is empty, it's going to be at least positive 2. And ideally, if this is easy, 1, 2, 3, 4, 5, 6, 7 3D electrons, all right? So if you count, starting with scantium, this would be 3D1, titanium 3D2, 3, 4, 5, 6, 7. 3D7 is what cobalt has. Neutral cobalt would be 4s2, 3D7. But we have here cobalt plus 2. First 2 electrons would come out of there. It looks to me like this is cobalt plus 2. If you don't believe me, and I totally understand, do the other ones, all right? So iron plus 3, first 2 electrons out of here would be 3d5. Nickel is 4s2 3d8, first 2 electrons out here, so nickel 2 plus would have a 3d8 configuration. But notice how I first noticed which period we're in, all right? It's in the period 4, it's a 3D element, so it's not going to be rhodium, and calcium, a main group metal, doesn't have enough electrons. So then I literally counted up the number of D electrons, which was 7, and I just counted on the periodic table. 1, 2, 3, 4, 5, 6, 7. So cobalt, neutral cobalt, would have 4s2 3d7, but this is cobalt with a positive 2 charge, so those electrons are gone. Cobalt 3d7. Any questions on that? All right. The last topic we'll talk about in this chapter is a little bit, I have to be careful here. I've got some strong opinions. It's a little bit, it has a little bit more positives or negatives, a little bit more give to it, shall we say. But there are some times that it's really useful, and so that's why even I include it here. And this last topic of Chem 221 is called periodic trends. Now, up here on the board, I have an incredibly cheesy periodic table. And a periodic table is like a rectangle. Hydrogen in the far left, helium, or in the far left, and helium in the far right, upper right, radon, lower right, and francium, FR, lower left. All right? And that's what they both are. Now, anything in this next section, we're going to talk about relating to size. Sizes of atoms, sizes of ions, atoms trends, and stuff like that. All of the sizes increase as you go left and down. All right? So if our conversations have anything to do with size in the next slides, ion size, atom size, etc., they increase as you go left and down. So Daniel comes up to me when I haven't even had my coffee yet. And I always have coffee, so that's silly. But anyway, let's say that he says, Russell, is calcium or cesium bigger? Like, I know, okay. Oh, I mean, of course, I have a PhD. I know all kinds of things. Here's my trick. Left and down, all right? So cesium is more left on the periodic table than calcium. Cesium is also more down on the periodic table than calcium. So I'd say, well, Daniel, cesium is bigger. And he'd be like, wow, Dr. Russell, you are so cool. You know all my secrets now, man. All right, I'm giving them all up here. Left and down. Nitrogen smaller than potassium, all right? Aluminum bigger than, say, fluorine, all right? Someone's thinking in this room, what about boron versus silicon? Because boron is more left and silicon is more down. Honestly, I'm not going to ask you those kind of questions. That's dirty poker. However, if someone from Chem 104 asks you, usually down is bigger than left, all right? So that's an informal way to do it. So if I was asked in the hallway by a Chem 104 student, I'd say, well, probably silicon is better. But I would also want to use Google here to check it out to make sure. So all these things with sizes, generally, left and down is bigger. There are exceptions. It's not a perfect rule, but again, generally without access to Google and stuff, that's a pretty good way to think about things. Questions on that? Yeah.
So right off the bat, you go helium to hydrogen.
Right. You'd say that hydrogen was probably going to be bigger because it's more left on the periodic table.
Proton versus proton?
Yeah. The attraction of the 2 protons to the 2 electrons is actually stronger than the single proton to the single electron. Yeah. And so generally that's what you see. Now, Daniel, like I said, there are exceptions to this, and that's why I get a little nervous talking about it, because it's not for sure, okay? But more often than not, left and down is the way to shoot.
But that includes the electron speed, right?
That's right, exactly. That's right, yeah, good question. It's the a radius in here is the distance from the center of the nucleus to the outermost electron. And so if it was sodium plus versus magnesium 2 plus, left and down, sodium would be bigger than magnesium in theory, okay? Right. Questions? Okay. The other two periodic trends, which are important in this chapter, and for stuff we're going to talk about, ionization energy and electron affinity. Now, ionization energy is an energy cost you have to add to make an electron go away from an atom. So making sodium to sodium plus, you pay a little bit of ionization energy. It's usually endothermic, all right? Electron affinity is actually a number you get as energy you get off when certain atoms absorb electrons. So chlorine and fluorine, for example, love gaining an electron to become chloride or fluoride. You actually will get some energy out of those. That's what electron affinity is. Now, I'm also going to, on the slide here, put a third term, which is electronegativity. And electronegativity is something that several of you in your presentations last Wednesday talked about, which were awesome, by the way. Electronegativity is another way to gauge how much an atom wants an electron. Anyway, so for electronegativity, which I probably won't mention again, electron affinity and ionization energy, those will all increase up and to the right. So while the sizes were left and down to get bigger, all of these other ones up and to the right. So if you're curious, which has the larger ionization energy, potassium or cesium, up and to the right, potassium would have the larger ionization energy. Same thing for these guys. So chlorine has a bigger electron affinity than sulfur because it's more up and to the right. That's really all these periodic trends are all about. And everything I'm going to say after this is basically just cool videos and fun ways to kind of talk about it, and also some warnings about sizes differences and stuff. So, questions before I go further? Yeah.
So the ionization energy is kind of like the opposite of the electron affinity in a way?
Yes.
The opposite thing is happening?
Yeah, that's right. Ionization energy is almost always endothermic, and electron affinity, more often than not anyway, is exothermic. Electron affinity is kind of a wishy-washy thing, but generally speaking, yeah, that would be a fair statement to make. Okay. The reason for all of these, which goes back to what Daniel was asking about earlier, is that as you go down the periodic table, the orbitals get larger, all right? N values get bigger, N2, 3, 4, 5, and the electrons are not held on quite as tightly. So you see the bigger atoms down here, those outer electrons just aren't held on very much by their protons. On the other hand, as you go more to the right, more protons in the same shell, they actually pull a little tighter. So electrons are held a little bit more tighter generally as you move to the right. That's generally why these trends happen. But again, there are exceptions. And again, with your, in this 21st century day, man, you should look up on Google and stuff, these kind of references, just to make sure that what you're spouting is actually the way things are. And I'll show you some exceptions here coming up. This is the handout that I have in your online stuff, but it basically is just this thing right here. There's also ways to talk about metallic character, which is the ability to lose electrons. It's all the same kind of thing. Again, it's all about going left and down for size, or most of these other ones up and to the right. So size gets bigger as you go down a group and left. They're added further from the nucleus, less attraction, size increases as you go left. Here's the different group 1 period. So this is hydrogen, helium, or lithium, excuse me, sodium, potassium, rubidium, cesium. And you can see as you go down the group, these numbers here are actually radii. They're radii in picometers. And so they are getting bigger. So sodium is about 186 picometers. And then down here to cesium, it's 265. So they do get larger as you go down. Going down a periodic table is usually pretty consistent, all right? Because you go down, you get a bigger N, and the atoms do get bigger. It's kind of this weird curve thing you see going down here. Now, as you go across the trend, it's not always quite as simple. But generally, so this is about size, remember? Size is left and down. So if you start on the right and go left, all right, the numbers are generally getting bigger, which is cool. And most of the time, that's what happens. So going left and down, sizes get bigger, all right? Again, there are some exceptions and stuff like that. The elements, well, size actually decreases as you go down. They're held on tighter, like Daniel asked about earlier. But again, generally speaking, left and down, bigger, up and right, smaller. This is a table with all kinds of different atoms. I put it up here because what we just saw, generally speaking, going left and down, things get bigger. So 99, 104, 115 is great. But look down here at this one. Tellurium is 143 and antimony 141. So left and down, it's actually getting smaller, not bigger, all right? And that's why these are called trends. They're not rules, because it's not consistently the case. Like here it's getting bigger, but then it gets smaller, and then it gets bigger again. And even in the top row, fluorine is a little bigger than oxygen, so it's not getting bigger consistently. But again, if you look at the overall periodic table, this is a pretty good trend. But that's why, as I said, if someone asks you, and it's really important, you better go look this stuff up just to make sure you're not in one of these little anomalies. So more often than not, left and down works really well for size. It works really well going down the periodic table. All right, like I don't know off the top of my head anyway of any exceptions to that. But going left, sometimes you do run into these little hiccups and stuff. So just FYI. So here's a kind of question you might see, all right? Comparing sodium, boron, aluminum, and carbon, which has the largest radius, largest size, left and down. I see several of you looking at the periodic table, which is really cool. So yeah, so on the periodic table, sodium is the metal. It's on the far left. That's going to be a good bet for this one. All right, it's most left and down on the periodic table. So aluminum, boron, carbon, you can see it kind of goes carbon, boron, aluminum over to sodium. Sodium is more left and down from the rest of them. Questions on that? Now, the sizes of ions, it follows a similar trend. It's kind of interesting. So let's say you had a lithium atom, and lithium has 3 protons, and neutral lithium has 3 electrons. The question is, if you lose an electron to become lithium plus, does it become bigger or smaller? Now, in this discussion, I like to think as protons as parents and electrons as children. And if you've ever been to a children's birthday party, anyway, sometimes the kids get kind of crazy, like Chuck E. Cheese's when it was open, places like that. But if you have like 3 parents and 3 kids, then the kids can't get away with much, all right? On the other hand, I've been to birthday parties and there were like, 4 parents and like 12 kids. And man, it was chaos and it's exciting. I'm glad they're having a good time, don't get me wrong. But as you have less parents looking at the kids can get a little crazier, all right? So if you make a cation, it's like taking away one of the children. So now you have 3 parent protons and only 2 kids. Those kids aren't going to be able to do anything. So their freedom, if you will, is reduced quite a bit. That's a really stupid analogy. However, what is important here, cations, positively charged ions, will be smaller than the atoms they come from. And that's just because, back to what Daniel was saying, you've got more protons relative to the number of electrons now. So those electrons are literally pulled in a little tighter, all right? You can use my analogy of parents and kids, and there's less kids relative to the parent protons, but really it's just about electrons being pulled in a little bit more. So in this case, the size will decrease. So lithium plus is smaller than lithium. Magnesium 2 plus is smaller than magnesium. Iron plus 5 is smaller than iron. All right? All of these kind of patterns exist. Cations will be smaller than the atoms they came from. Questions on that? Now, the opposite can happen too. fluorine becomes fluoride. F neutral becomes F minus 1. So where before you had 9 electrons and 9 protons, now you're still going to have 9 protons because that's what defines fluorine, but you're going to have 10 electrons. And at a birthday party with more kids, they tend to get a little crazier, which is cool. So in this case, the ions will actually be larger than the atoms they came from. Anions are bigger than the atoms they come from. There's more room for the electrons to run around. Now, reality, it's all about positives and negatives. You have fewer positives for more negatives, so they tend to drift a little bit farther. So while cations, positive ions, are smaller, the anions, on the other hand, are larger. The protons just don't pull the electrons in quite as well when there's more electrons than protons. And to the best of my knowledge, all anions are bigger than the atoms that they came from. All right? So cations are smaller than the atoms they came from. Anions are larger than the atoms they came from. So what it comes down to is if you're looking at ions, all right, sodium versus magnesium, sodium plus 1 versus magnesium 2 plus, or oxide O minus 2 versus fluoride F minus 1, the trends will apply. You have to just compare cations to cations and anions to anions. The anions are automatically going to be bigger than the cations they came from. So here's the kind of questions you might have for anions. I might ask you, well, which is bigger, sulfide or chloride? Well, sulfide, size, bigger, more to the left and down. We would predict sulfide would be bigger than chloride. I might also ask you, is potassium ion bigger than calcium ion? And you would say yes, because K plus is bigger than Ca2 plus, more left than down. But I wouldn't ask you, is potassium K plus bigger than chloride, Cl minus? Because anions are automatically bigger than the metals, the atoms they came from, and cations are smaller. So that would be a disconnect for this kind of conversation. But if you're comparing anions to anions, or cations to cations, then all these rules still apply, left and down, and you're good to go. Questions? Here are some neutral atoms, like this little circle right here, or this little part right here, and then the cations or anions. So that you can see like 113 to 34, beryllium positive 2 is much smaller than beryllium. Lithium plus is bigger than beryllium 2 plus, just like the lithium atom is bigger than the beryllium atom, all right? But over here now, fluoride is actually a pretty big anion. I can't compare fluoride to the beryllium positive 2, only anions to anions, cations to cations. But generally speaking, left and down, although actually here's an exception I just saw right now, so maybe it's not quite as cool. Anyway, these are trends. They're a little cheesy, like I said. But if you have to guess, someone in the hallway accosts you, then you can at least give them a rational answer. But double check with Google just to make sure. Okay, so which one of these would have the largest radius? Okay, now argon has 18 electrons. And if you do the math, all of these have 18 electrons as well. Like chlorine is 17 plus 1, 18. Sulfur is 16 plus 2. Phosphorus, 15 plus 3. So all of these have the same number of electrons, all right? But largest radius, the quick and dirty way, left and down. Which one of these four is most left and down? Phosphorus, right on. Argon, chlorine, sulfur, phosphorus, left and down. Left would be phosphorus. So this cheesy thing I'm introducing here says you should pick phosphorus. Now why phosphorus is bigger? Phosphorus has 15 protons and 18 electrons. So a lot more electrons, kids running around for 15 proton parents. Definitely phosphide, would have the largest radius, all right? So you can rationalize it in that you have a lot more electrons relative to protons in phosphide, or you can just say left and down. And as long as you're comparing anions to anions, or cations to cations, left and down works really well, more often than not. Questions? Now, a redox reaction, as we saw earlier, something has to lose electrons, something has to gain electrons. And magnesium loves to lose 2 electrons. But why does magnesium lose only 2 electrons and not, like, for example, 3 electrons? And why do nonmetals take on electrons usually instead of giving them up? And those are questions we can answer with these other periodic trends. Now, the ionization energy is the first one we're going to look at. And like I kind of babbled about earlier, it's a positive endothermic energy required to remove an electron. Now, the energy required to remove the first electron is the first ionization energy, and the energy required to move the second electron would be second ionization energy, etc., etc.
To remove the outermost electron from a magnesium atom requires 738 kilojoules of energy per mole.
So to turn the neon 3s2 configuration into a neon 3s1 configuration, you add 738 kilojoules of energy per mole. All right, that's how much it takes to get magnesium to magnesium plus 1. But as we've seen, magnesium likes to be magnesium plus 2. Now to do that, you have to add an additional amount of energy. And notice it takes more energy now because you still have the same number of protons, 12, but now you have only 11 electrons. Those proton parents are pulling on those electrons more than you did when there were 12 parent protons and 12 electrons. So the energy cost has gone up, removing the second electron.
Removing the second electron requires more energy, 1,451 kilojoules per mole.
If you add these two numbers together, it's roughly 2,100, 2,200 kilojoules per mole, which is a lot of energy, but it is an energy which is doable, all right? With normal things at room temperature, that's not unusual. Here's the energy to take magnesium positive 2 and make it magnesium positive 3. Now notice that these two together, 2,200 or so, 7,700 kilojoules to remove that third electron, make it magnesium plus 3. And that's a lot more energy. It's more than 3 times the energy required to move the first 2 electrons. So it's a pretty big energy jump going from magnesium positive 2 to magnesium positive 3.
To remove a third electron from magnesium requires much more energy, 7,733 kilojoules per mole.
This kind of energy bump is just not seen. You can do it in a lab, all right, if you have high-powered energy and stuff like that. You can make these happen. But in the real world, we never see magnesium positive 3. It's not that you can't make it, it's just the energy gap is pretty heavy. So for most of these metals, the main group metals, like all the group 1s, positive 1, because the energy required to remove that first electron is doable. But when you get to the ones that aren't doable, like turning, say, sodium plus 1 to sodium plus 2, then you'd have some number like this. It's quite a bit more energy to make it happen. So ionization energy is one way you can rationalize why group 2A are always positive 2 metals and why aluminum is usually plus 3 and stuff like that. There's like mellow, 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 and then a big jump to get to that forbidden one. And that's why we don't usually see them. So this is a graph showing ionization energy trends. Now, all the rest of these periodic trends, generally up and to the right is how they increase, all right? These aren't quite as nice as the size ones. So for example, in here, you can see on the right, going from potassium to chrysolite, I mean, it's more up, more of an increase, but like it went from arsenic up to selenium down, phosphorus up to sulfur, nitrogen to oxygen. So it's not quite as nice as the size ones. That's why I always get kind of periodic trends. I'll even talk about them, but there are uses for them, and they are used a lot of times for doing it. These are all first ionization energy, supposedly. Notice how helium and neon are the highest ones. That's why nobody's made compounds with them, all right? The energy required to remove an electron is so high, and they're already so happy since they have filled orbitals that they don't want to play with anybody, basically. Anyway. So again, generally up and to the right when it comes to these, but they're a little shakier than the sizes ones were. Moves up and down. Metals lose electrons more easily than nonmetals. That's totally what you see too. The lower ones are the metals and the higher ones are the nonmetals. So it takes a heck of a lot more energy to make oxygen, oxygen plus 1, than it does sodium, sodium plus 1. Metals are great reducing agents. They love to give up their electrons, while on the other hand, nonmetals will only lose their electrons if you really pound on them. And generally they won't let you do that. The energy cost is too high, all right? So this is one. Ionization energy can be used then to explain why atoms lose electrons, and also why the nonmetals generally don't lose electrons. The energy costs are just too high. Now again, the punchline of this whole area, anything with size increases left and down on the periodic table, and the rest of these, ionization energy as well as electron affinity, they will increase up and to the right generally. This is kind of a fun thing. This is lithium, sodium, potassium, all group 1A metals, all right? And group 1A metals, the ionization energy increases up and to the right. So that means that the lower ones are going to be a little bit easier to make things happen. So check out the differences in reactivity.
Lithium is the first of the group 1A metals. It reacts with water to form lithium plus 1 ions, losing an electron from a 2s orbital. Compared with sodium and potassium, lithium reacts rather slowly. Sodium is the second of the group 1A metals, occupying a position just below lithium on the periodic table. When it reacts with water, it loses an electron from its 3s orbital. The reaction of sodium with water is more vigorous than that of lithium. Potassium is the third metal in group 1A. Lower than both sodium and lithium on the periodic table, it is even more reactive with water. The valence electron lost by potassium upon reaction with water comes from a 4s orbital.
One time I did a thing in lab, I was using sodium and potassium, and sodium was kind of like boring, so I thought, oh, well, we'll try with potassium. Oh my gosh, it jumped out of the water, and we had one of these things at the time over it, and it broke through it and stuff like that. So I'm very respectful of the reactivity of the alkali metals. You can see the little purple thing right there, that's the color of potassium, which is kind of cool. This is just kind of for fun here, so I'll show you this.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Each one of those tanks was supposedly 3,500 pounds of sodium, and I can't even imagine that much going off in water at one time. And I think it's a wonderful pyrotechnic display, and I'm also pleased they're using it for peaceful uses and not war, all right? However, sodium with water makes sodium hydroxide, which is very basic, all right? And you put that much sodium in water, any kind of lake, I mean, it's going to kill it. It said there were no fish, Anyway, it's going to make it so basic that nothing could survive there. And I also worry about the groundwater, like leaking through to the Columbia. I'm not totally sure where Lake Lenore, Washington is, but that's obviously our neck of the woods. So I'm very nervous environmentally about what they did at this time. But as I said, it's also good. They didn't have to use it in war and stuff like that, which is cool. But anyway, you can at least appreciate the questions that come around with them. Anyway, let's move on. Electron affinity is the last one we're going to look at. And electron affinity is the energy released upon a neutral atom gaining an electron or electron. It's usually exothermic, so the energy are usually negative, but sometimes they're neutral ones too.
When a gaseous atom accepts an electron to become an anion, the energy it releases is a measure of its electron affinity. For chlorine, this is minus 349.0 kilojoules per mole.
Notice how chloride became bigger from going from chlorine to chloride, more electrons relative to protons and stuff like that. So again, the electron affinity is just a measure of the energy that happens when an atom gains an electron. Now, these are the electron affinity values that are usually represented. People usually keep the noble gases out of these discussions because electrons don't usually go well with noble gases. So in my cheesy picture, or the cheesy pictures that are used for periodic trends, for these guys, you should think about fluorine or chlorine as being the maximum. Now, no one's clear why chlorine has a bigger electron affinity, more negative electron affinity than fluorine does, but more or less you can see it kind of increases up and to the right. This is the weakest, I think, of all the periodic trends. Electron affinity is interesting, but we won't use it that much overall. Electron affinity is also technically a negative number, so we're thinking about it here as an absolute value, which is even more confusing. That's why, honestly, we're not going to do much with electron affinity in the future, but it can be used to justify why chlorine and fluorine like becoming negative, and these guys down here don't usually like being negative. So again, electron affinity generally increases, the absolute value increases as you go up and to the right, but again, there's lots of weaknesses in the trends and stuff like that. Here's another little graph. You can see that kind of more or less up and to the left, but there's problems. Why chlorine has a bigger electron affinity than fluorine is not clearly understood. We're going to assume in Chem 222, when we talk about electronegativity, how fluorine likes to gain electrons more than anything else. However, if you look at the raw data, then it's true, chlorine is bigger. That's another reason why this one drives me crazy. Anyway.
The reaction of sodium and chlorine is governed by the arrangement of the electrons of each species about its nucleus. Chlorine is an oxidizing agent because it has a high electron affinity. Sodium is a reducing agent because it has a low ionization energy. The redox reaction produces the ionic compound sodium chloride, which contains one sodium ion and one chloride ion.
So since Chem 220, the beginning of this class, when we started talking about like sodium chloride, it was always like sodium gives up an electron, chlorine takes that electron in. Well, now we can get a little fancier. Metals have relatively low ionization energy, which makes them easier for them to lose their electrons. On the other hand, a lot of the nonmetals really like to gain electrons. They actually give up energy gaining electrons. That's what electron affinity is all about. So it's a good match. And if you have a low enough ionization energy and a high enough electron affinity, then they will share electrons like that pretty easy, which is pretty cool. So this is just a fancier way then to justify the patterns that we've seen this whole quarter, stuff like that. Any questions? All right, that is it for Chapter 6, Part 2. So right on. So this is actually the end of the material part of Chem 221. Of course, we don't have lab on Wednesday. Next week, Monday, for a lecture, I will have like a review session, which is more practice over Chapter 6 stuff, basically. And then the last lab will be Wednesday, as well as problem set 6, last quiz and stuff like that. So we're getting down there, which is pretty exciting. If you had time over Thanksgiving and you want to look at any of this stuff, of course it's cool. But more importantly, I hope you all have a great Thanksgiving. Thank you for being here today. I will see you next week, Monday. Have a great day. Have a wonderful Thanksgiving.